Good morning, ladies and gentlemen. Today is yet another switch off topic. Though we have covered already several topics, we've been talking about scattering electrons and basically disregarded electron-electron interaction. We've been explicit about this. If you recall, the real justification is not that electrons do not interact, but key explanation is that electrons are quasi-electrons, quasi-particles in matter. And these quasi-particles do not interact closer to Fermi surface. Nevertheless, there are conditions, there are phenomena when electron-electron interaction is crucially important in quantum transport. This area, this concept, is commonly called Coulomb blockade. And today we will be talking about Coulomb blockade. Let me, as usual, quickly sketch outline. We will start with basics. We will understand that charge, since it is produced by elementary particles, which can be counted, is quantized. And there's charging energy associated with charging structure parts, right? We need some islands to store charge in, separated by barriers, which are high enough to have well-defined charge. And what is interesting in Coulomb blockade concept, you can kind of build up good description, good understanding of transport, starting with very simple concepts, just kind of self-consistent theory. You don't have to know much of quantum mechanics even. You just begin to reason, and you can describe quite complex phenomena, experimentally relevant phenomena, from this line of reasoning, just from a concept of charge quantization. Right, that includes some capacitive circuits, and we kind of recall how to make capacitive circuits, how to solve them. Central nanostructure in this concept is, in this context, is single-electron transistor. We will understand what are transport phenomena in this single-electron transistor. Then we look at manifestations. Coulomb diamonds first. We look a bit at master equation, general stochastic equation, which is valid for many areas, how it works in Coulomb blockade. Right, and we will look at some manifestations, experimental signatures of Coulomb blockade. Generally, Coulomb blockade is seen in almost any nanostructure where you have at least two tunnel barriers. Let's recall this, and then we'll let us make a note of this, and then we will see the examples. Good. What would be also an interesting starting story? Again, about cheating, we should be subject to solid state physics. Electrons do interact, but you consider during the course, 99% of non-interactive particles. All right? Thinking of band structure, all the stuff, it's all about non-interactive particles. That's because, first, it's too complex to analyze what happens with interaction. Second, due to the fact that electrons are converted to quasi-particles, for most materials, it's not really relevant. The long interaction at a conceptual level can be safely disregarded in many materials. So it is too complex to describe. In quantum transport, it's just opposite, I could say. Coulomb blockade is frequently relevant for transport, and it's very easy to describe. Much easier than, for instance, Landauer formula or quantum scattering. So let's go for that. First of all, let us imagine that we have a metal droplet. So that yellow thing is a metal, good conductor, which hangs somewhere in vacuum, completely isolated from anything. Who can recall some realization, some experiment about such things? To check about history of physics. How people have discovered electrons. No, it doesn't anymore. It's very kind of popular experiment and very simple. I guess it's one of the best experiments in physics at all. So let me perhaps spend half a minute on that. There was a professor in America called Millikan. Does it ring a bell? No? Okay. That was the end of 19th century. But still, okay, they have microscopes, for instance. What the professor did, he looked with a microscope onto, how do you call it, suspension of very simple oil droplets in air. Okay? Isolated oil droplets hanging in air. So he looked at it in the microscope, and he followed the motion of these droplets in electric field. All right. Suppose you do this experiment, what do you expect?
Nothing happens.
That wouldn't make it sterling.
So they must be maybe statically charged, so they move.
Yeah. Okay. Right. So since there was an effect of electric field, yes, they could have charge. Some of them. What is so special about this charge? What was discovered, Professor Millikan, that the charge is quantized. So looking at microscope, so roughly he could see that many droplets do not move at all. Some of them move upwards with certain velocity, some move downwards, some move perhaps twice the velocity, right? That's how the quantization of electric charge has been discovered. That was possible to see physical effects from single electrons. And Coulomb blockade kind of just put it in the context of nanostructures. So again, it's better not to think about oil, but conducting material. What will happen if you put one extra charge into this island, right? So electrons kind of form a liquid, they collective. So this charge will go to the surface of the island, right? That's what you expect from any metal. You put charge into a metal, it will go to the surface. Then inside the metal, interaction is great. And there's a good reason to forget about interaction inside. Let us see what happens outside. If there's a charged body, there's an electric field around this body. This electric field costs energy, right? Best way to express this energy is to regard this island as a capacitor. You remember, capacitor is something where energy depends on charge quadratically, and the coefficient is actually inverse capacitance. Fine, so there's electrostatic energy associated with charge into this island, and it's important to note that charge is quantized in units of electron charge. So that's what we have. If you want to put extra charge into this island, we have to make work, whatever. We have to supply energy. Good, energy, there's a certain scale associated with energy. Charging energy, say we put one electron, how much energy do we pay? Let us compare it with another energy scale in this island. What is this energy scale? All right, so it is an isolated system, so that quantum levels in this system are discrete. The levels are discrete, and I would like to estimate average level, splitting average level distance in this metal. Fine, all right, many ways to estimate this. Let me present one. Let us, to be concrete, take some island, which is not very small, more than several atoms, but not very big. So let me talk about 100 nanometer island. Then I can't count number of atoms in this island, interatomic distance. What is this? Would be good approximation. Angstrom, which is 0.1 nanometer. Fine, that gives me 10 to the 9 atoms. Right, then I remember there's a Fermi energy, which is of a scale of several electron volts. And there's usually several electrons per atom. Let me think of 1 electron per atom. Good, so to get level splitting, I divide this energy band by the total number of atoms. That's estimation for level splitting. Well, it is very small. So it would be practically, it means that at more than level of instrumentation, you cannot resolve levels which are so close. 10 to the minus electron volt. Good, let me estimate what is this charging energy. Right, again, I use, I guess, illegal formulas for capacitance. It's not in C units, but all system units agree that it is inversely proportional to charging energy is inversely proportional to the length. Capacitance is proportional to the length in this case. Right, so I estimate the length as number of atoms to the power of 1/3. Good, so and the whole estimation is 1 milli-electron volt. So it's many orders of magnitude larger. So one could try to change the scale. One could try to find the size at which charging energy is of the order of this level split chain. What do you expect at which scale this will happen?
Very big island.
No.
Very small island.
Very small island. How small is very small? We could think about this in atomic units, where all energies are measured in atomic, how to say it, Rydbergs in atomic energy scale. And all lengths are measured in the units of interatomic space, or radius. Good. In this case, this delta is just 1 over n, while charging energy is 1 over n to the power 1/3. Fine. Then these two scales become of the same order.
When n is around 1?
Precisely. So eventually Coulomb blockade can be compared with level splitting only at atomic scale. Very good. What I want to say, and this explains the term Coulomb blockade, which otherwise looks too fancy. So Coulomb, that's because of Coulomb law governing the electricity at the scale. Blockade is because you have to pass this energy to put electrons to the island. And if you don't have this energy, if you don't apply sufficient voltage, if temperature is low, if this energy is not available, the transport is blocked. Good. Let me get to nanostructures, to the devices. It also allows building some small, tiny little devices which do something, right? So that's the simplest device, which is called Single-electron box. There are 3 elements in this device. First of all, the island, which we consider to be isolated, but if it's completely isolated, it's boring because we cannot change the number of electrons in this island. Good. In order to be able to do so, we put this island close to the metallic electrode, close to a lead, so electrons can jump back and forth. right? We want to control this number, and that we do with yet another electrode, gate electrode. So we set voltage difference between this electrode that can be grounded and the gate. Then you feel what happens. There's electric field here, and this electric field tries to put more electrons to the island. Or if you switch polarity, it tries to repel electrons from the island. Okay, how to quantify this? It is a problem of capacitance circuits. So we have capacitance between island and metal, and between island, this capacitance, and gate electrode. Right. We have voltage source. What differs from standard capacitive schemes, we have fixed charge in the island. What does it mean? So there are capacitances, there's opposite charge here. Let me call it, for instance, Q1 at this side. So that must be minus Q1 at this side, right? Remember, same for the second one. Q1, Q2 minus Q2. So then the difference of Q2 and Q1 must be N. Good. So one has to find charge and energy under this condition. And this is the answer. It is proportional to N squared, that we already know, that we have seen. But with an offset, which is set by gate voltage. It's natural that gate voltage makes certain N energetically favorable. This combination is sometimes called induced charge. Induced charge divided by elementary charge. Right. Good. Let me go step by step. We are not in a hurry yet. Let me plot energy of different charge configurations versus this parameter, versus gate voltage. For any given N, the plot is a parabola. So what I have here is a set of parabolas. They shifted in gate voltage corresponding to induced charge 1. So now I want to understand what the ground state of the system, what's the most energetically favorable state. To this end, I look at the system of parabolas and accurately connect lowermost pieces of all parabolas. Fine. That will give me actual energy of the system. And as you see, it's kind of oscillates as a function of gate voltage, right? What are the cusps? What are jumps? Right? It switches from one parabola to another parabola, and it means that the number of charges changes abruptly. So what you have here is a staircase, average kind of energetically favorable number of charges changes in step like fashion as a function of gate voltage. Right, that's single electron box. There's no transport yet. We will go towards transport, but let me first reason about this connection, about this barrier. It's counter-controversy. If I would make this barrier, if I would set it at a big distance from the metal, there will be always tunneling, say once a week, electron goes there. That seemed to be safe. Charge is quantized. Good, but suppose one would just make a metallic shortcut between the island and metal. Then we cannot say that the charge in the island is quantized, right? Because, right, it's just a big piece of metal completely connected. So one has to ponder a bit this question. Right, so in practice, and it's one how first circuits of this type have been generated, in practice, while doing with metals, people use oxide barriers, thin oxide barriers. For instance, one of the schemes which is used till now, it's evaporation made in stages. So suppose we have a substrate, insulating substrate, and we have an ability to evaporate metal films into the substrate. Then we first evaporate, for instance, two leads. Here and here. Then we kind of expose it to oxygen, for instance. So oxide layer is formed at the surface of the leads. Then we put the island on the top of this. That's will form, if you look from the side, an overlap junction. So there will be oxide between metallic films. Right, if one wants to make it clean, well, one also removes oxide from these spots, but it remains under another metal layer. Fine. It is very interesting condition on this barrier, which also illustrates nicely the universality of quantum transport. One could think it's some material property, depends on atoms from which you make the structure. Nothing of the kind. So eventually, the final answer is a total resistance, total conductance of this contact between ions and metal. How can I reason about this? I could utilize here Heisenberg uncertainty relation. Let me have charge and energy. We which is E squared divided by C divided by capacitance. And let me estimate the typical time of discharge of this pilot. Assuming this is classical conductor, everything is fine. This is RC time, product of resistance and capacitance. Now, Heisenberg uncertainty relation. The uncertainty in energy is, let us see, small if the product of energy times time is small. It has to be compared with h bar, with Planck constant. All right. Heisenberg uncertainty relation. So we substitute here charge and energy and RC time, and capacitance eventually cancels out. And we understand that in order to have well-defined charge and energy, the resistance has to be large enough, larger than this combination. Okay, we have already seen that it is nothing but inverse conductance quantum. So in other terms, in other words, the conductance has to be smaller than conductance quantum. Good, that's about a shortcut. Another story is that voltages and temperatures which are involved in transport must be smaller or comparable with charge and energy. If temperatures are bigger, what will happen? We will have very many charging states available, and you would hardly see any quantization. Good. Since I want to do transport, let me have fun. I drew precisely the same structure which I explained when I'm talking about fabrication, but I just present it in terms of a circuit. It is kind of a blessing that one can put quantum transport systems into circuits which look like classical circuits. What is a circuit? This is the island, central part of our device. So it has a discrete number of electrons and each state. Right, there are two leads, left lead and right lead, two junctions, two capacitances between the lead and the island. All right, I want to have extra functionality. I want to have a gate electrode which affects the island. So here it is, this gate circuit. Right, so in order to compute energy balance, we only need to know these capacitances, three capacitances. Then how we proceed? Well, as far as energy is concerned, it's no wonder that all capacitances which are adjacent to the island just add together. Right. As to this Q induced charge, it is also democratically added by all voltages, including corresponding capacitances. Right. So now we can compute energy differences. Remember, energy by itself hardly makes a sense because you can choose arbitrary reference point when measuring energies. Energy differences do make sense, right? So we can compute, for instance, an energy which is required to add one electron. Yeah, here it is. What's important for me to note now, it's linear function of the intercharge and induced charge. I will use assume that this is linear function, but otherwise it's just energy. Right. Let me kind of take the problem as it stands. Let me talk about possible energy transfers in this single electron transistor. Okay, basically we want to organize transport of electrons from one lead to another lead. They have to jump to the island and jump out of the island. Or transport could go in opposite direction. That gives us 4 possible processes for electron transfers, which I put in different as arrows of different color. Right. So there are 2 processes from the left and to the left, 2 processes from to the right, involving different junctions. Okay, now a little bit concentration, how to compute the energy differences associated with these processes. First of all, we have this energy differences we have just computed. Is it all? Well, it could have been everything if we were gods and could create electrons with a snatch of our fingers. We don't have such an ability, but we can always take it from another electrode and put it to the island. That's why these energy differences also involve the potential, the static potential of corresponding lead. Good, so if I take it from the left, I have to take it with minus sign to the energy different. If I put it to the left, I put it with opposite sign, the same for the right. So when I'm computing the energy differences, I have to think, where do I put this electron? Where did I take it from? Fine. Good. So we know the energy differences, and let us see how does it work. What are possibilities? Very simple possibility, a little bit counterintuitive, but very simple, and that's why we call it Coulomb blockade. It could be that all these differences are positive. What does it mean? It means that at 0 temperature, there are no charge transfers, right? All stones roll downhill, no stones rolls uphill. All processes are accompanied with dissipation. So there will be no transport. Another interesting and fancy situation is the following. is the following. Suppose one of the energy differences is negative. For instance, if electron, for a process when electron comes from the left, okay? Then it will come to the island, it will sit here, right? And if the energy difference to the right is negative, it will jump further. But there is a little bit of a point. This energy difference is already for a different number of electrons, because electron has come and sits there. Yeah. And if I look at energy difference of transfer from the left at the same charge configuration, it can also be positive, which means electron sits there and it blocks all other electrons from coming. That's not what we see in scattering approach when all electrons went through the structure independently, right? It's manifestation of interaction. Fine. Let me get to Coulomb diamonds before we go for the break. Right, in many languages, diamonds or similar word means precious stone, right? But believe me or not, English is exception. So how would you translate diamond to Dutch or German?
Right.
Yeah, or rhomb. So it's just geometrical figure. And this geometrical figure we see here. First of all, in which space, in which plane? We have basically two axes. We have induced charge due to the gate and all other electrons, and bias voltage between two bits. Two parameters. And that diamond gives a region in this plane where it's energetically favorable to have certain number of electrons and no transport. All four energy differences are negative. Okay, how to get it? It's important for me again that there's a linear dependence of these energy differences on voltages, which means that the condition that energy difference is zero is a line in this plane. Okay, I have four rates, four conditions. So to fulfill all the conditions, I just, I call it, I grave this figure from the plane. Good, that I did for a certain number of electrons, say n equals 0. If I do it for n1, 2, -1, -2, I would just produce the same figures, but shifted by 1. So let me show the full figure. So there are diamonds where no current would occur. Good. So it's a kind of a cartoon, it's a sketch. Here it's real current, or whatever, what is that? Okay, conductance, color map of conductance, versus gate voltage and versus bias voltage. So black, no conductance at all, diamonds and colored are high conductance. My question is if this particular picture experimental or theoretical. Just guess.
I guess theoretical.
Yeah, why?
I mean, the top of the triangle looks just a bit too sharp to be really experimental data.
I would say it's too pretty, too accurate to be experimental. Right, it's theoretical data. What was the question?
Why? Because when the energy goes up enough that we have this transport channel in between the two occupations of the leads, why doesn't the conductance go up stepwise? Because we only have one. Why doesn't it go up once when one channel enters the bias window? And
Yeah. Yes, it's good question, and we will talk about this when we look at tunneling rates. By now, I suggest we have a short break, like 7 minutes perhaps.
Over the second quantization and the.
Good. So now let us try to quantify this conductance, this current. So how do we do this? What is general approach to this? It's the approach is very general indeed. It is a master equation approach, which is good for any stochastic processes starting from, I don't know, processes in the at Big Bang, at the origin of our university, till processes which occur in the context of financial bookkeeping. All can be described with master equation. Right. First of all, let us specify to our situation, we have different states of our island. Those are labeled with number of electrons in this island, discrete label. It's important for me to say explicitly that quantum coherence between the states has been lost, because there are many electrons which can tunnel back and forth in many states. Level splitting, as we mentioned, is much smaller than Coulomb blockade. So these states are just classical states. Fine. So in this situation, we can characterize the system by probability to be in a given state n. Fine. Since electron transfers are stochastic. So what we can say about this probability, if we know the rates, if we know the rates of the processes which change the electron. Who knows how to say a rate in Dutch? Verandering van waarschijnlijkheid per tijdsnelheid. So short. Right, indeed, red shows that the probability is changing, and this is per time unit. Right, so we look at the balance of probability to be in state n. And there are two types of processes occur, and this is general for a master equation approach. There are processes which reduce its probability. It's processes when the system goes from n to some other number of electrons. And the contribution of these processes is naturally proportional to probability to be in this state. And here is the total rate to so right here sum up processes going to the right, to the left, because they all change the number of electrons. Fine. Then there are income terms, right? So master equation is nothing but bookkeeping in physical terms. There are terms to spend probabilities, there are income terms. These processes are proportional to probabilities to be in different states with n+1 and -1. And there are corresponding rates which bring the system from n-1 to n+1 to n. These rates are different because all rates that depend on n, that depend on number of electrons in the element. Good, general scheme. That was that is for now for Coulomb blockade. Very simple, very similar scheme we discussed in lecture number 3 when we talked about Boltzmann equation in quantum transport. Fine. Let us recall that actually we want to compute current rather than probability to be in a certain state, how they are related. First of all, if all voltages are stationary, we expect stationary current, which means that the current in the left junction is precisely the same as the current in the right junction. Right, my statement, which is easy to understand, that the currents are expressed through probabilities to be in this states. For instance, let us look at the current through the left junction. There are two processes in this case, the tunneling from the left and to the left. They contribute to the current with opposite signs because electrons are transferred in opposite direction. And it's they're weighted with probabilities to be in certain states. So that's all logical. We have summation over all possible states. The same we have for the current in the right junction. And if I look at this formula, well, generally left junction is left junction, right junction is right junction. The rates can be very different. And if we compare left current and right current, there is no chance for these currents to be the same. From the other hand, I believe in conservation of particles, so they have to be the same. So who can resolve this small paradox for me? Okay. Let's go to the basics. When you're confronted with something, what is the first thing you do? Very general principle. How to live, sir? What's the first thing you do? Before any reaction, if you're vice person, if you don't want to react as animal. Come on, guys, what do you do? You accept what has happened. Only if you accept this, you can already react or do any actions. Let us accept that if these probabilities are arbitrary, currents are defined. Good. Let us recall that they have to be equal. That leads us to the conclusion that they will be equal for a particular choice of probabilities, which comes from the solution of master equation. It's kind of, if you wish, foolproof check of these equations. All right, you solve the question, you look at the current, if they are the same, you have solved it correctly. Good. Right. I should mention that I'm talking here about average currents, which are averaged over all statistical processes. That's why we can think of stationary currents. They're not supposed to depend on time. But let's not forget that they're contributed by discrete electron transfers. So if I would sketch a timeline, it's rather sharp peak, collection of sharp peaks at time moments of electron transfers. But if you average over these moments, and if you measure the current with real apparatus, which has all time delays, you cannot measure really instant current. You kind of always time average it. Fine. Let us now talk about the rates or something that has happened to these pictures. I guess I want to find different slides. Sure. How does it work? Okay. Good. So, to determine the rates, let's talk about tungsten metals. We have talked about tungsten already. Let us imagine a tunnel barrier and recall the tunnel barrier as we define it, just a transport channel or channels with very low transmission. Fine, so we can consider tunneling events as independent processes. They're separated by large time. What is, I would say, technological blessing, which allows to make very good and reliable tunnel junctions for nanoseconds. It is very peculiar property of aluminum, because you have heard about this. If we, for instance, take iron and expose to to hydrogen, what will happen? It will become oxide at a time scale of several years. Iron will disappear, it will be completely oxidized. Aluminum is different. If you expose aluminum to oxygen, the formation of oxide layer will be automatically stopped, right? And the resulting layer will be very thin indeed. It will be like 50 nanometers. So that is the reason aluminum is frequently used to make well-controllable and reliable tunnel junctions. Right, so let us see what will happen during the tunneling. There is no charging energy yet. Okay, energy diagram. Red color are filled electron states. Blue color are empty state. So we have two leads, left and right. We have energy shift, voltage applied, right? So number of electrons which are transmitted are proportional to the energy gap, energy strip available for tunneling, right? So one can compute the rate from the current, just number of electrons transferred, and this current is just given by tunnel conductance and voltage, which is energy width of the strip. Okay? Accept this, very simple. Let us take Coulomb blockade into account. Good, so now on the left I have a lead, and on the right I have an island. What will happen if an electron from the lead will enter the island? Okay, it cannot appear in the island at the same energy. It will appear at lower energy. Why?
It has to pay the charging energy. It has to pay the charging energy.
It has to pay the energy to charge the island. And its kinetic energy is the only source of this energy available. That's why actually it will go lower, and that reduces the energy strip available for tunneling. So here I put it, the actual rate in Coulomb blockade conditions, it is determined by the very same conductance. No other coefficients enter, and by the fact that energy strip is reduced. Good. That is that gives us rate which is proportional to energy difference, provided that energy difference is negative, right? We remember that at zero temperature, all processes with positive energy difference are suppressed. Good. If we allow for temperature, and that can be done with more sophisticated formulas, a little bit more sophisticated formulas, which take into account occupation numbers of electrons in the initial and final state. All right, so it will be such tunnel rate for finite temperature. You see there is some rate for positive, going on for positive energies as well, due to utilizing energy of temperature fluctuations, of thermal fluctuations. Right, so we know the tunnel rates. We can substitute it to master question and get the results. Somehow I go a little bit faster than, anyway, we still have many topics to discuss. So with this, let me describe experimental manifestations of Coulomb blockade. And as I said, Coulomb blockade is visible in many nanostructures. So there's also universal transport phenomena which can be seen in different nanostructures with different material size, etc. Right. So the simplest measurement which one can do with any physical system, not only with nanostructure, but with anything, you just connect the leads, the sample, and you apply small voltage. Then you change the parameter. In our case, it's gate voltage. So we look at linear conductance of the structure as a function of gate voltage. And what we see here is called Coulomb oscillations. Right? If temperature is really very small, no quantum effects are involved, that this picture is a picture of well-separated peaks. If temperature increases, then these peaks become wider. I have a formula for this which shows that the width of the peaks is proportional to temperature. So by these peaks, here simplest picture is to simplest way to understand this is to look at this picture. There is a situation when it costs more energy to add an electron or extract electron to another lead. Since voltage is low, one can regard the chemical potentials of the leads to be the same. All right, so both energies could go to zero at the same time. And in this case, you can organize electron transport through the leads, but both energies have to be the same. Let me perhaps kind of put the control question. We are back to Coulomb diamonds. Where are these points of conductance peaks? Where are conductance peaks in this picture?
We are cutting a line through the y0 axis because there's no bias voltage, and we're changing the gate voltage. So
yes,
we're going where the Coulomb diamonds cross the x-axis.
Yeah, precisely right. So how do we know this? Because the boundaries of the diamonds are defined by zeros of energy differences. So if two diamonds cross, it means that both the energy differences are zeros. So peaks are situated indeed here, 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 and here. And it's periodic. Right. Let me tell a little bit more about temperature dependence of the peaks. So if temperature is small, the peaks are narrow, as I explained. Well, there's a furnace as is. So these curves, red one and green one, are made for two low temperatures, and the peaks become wider, and eventually they merge. They merge up to this point. Right, what happens here? Here we have quite, and temperature is sufficiently low to provide us with many charging states, or in other words, the transfers through left and right junction can go to both directions. But let me talk about experimental facts. Although peaks merge and there are some fluctuations, it's not the whole story. Even after the peaks have merged, almost overlapping, there's still temperature dependence. So only at temperatures which are a bit 3 times higher, the conductance saturates at some level, and there's roughly a factor of 2 difference between these two levels. So there's temperature at which peaks merge, there's infinite temperatures, about a factor of 2 difference between conductances in this temperature rate. Okay, perhaps it's also a control question. We can try to explain this. Factor of 2 difference between, let me be a little bit more precise. So there's peak height in the regime of low temperatures. And there's a saturation value of saturated conductance and high temperature. And there's roughly factor of 2.
So for infinite temperatures, the peak width is approximately infinite. So we just get a horizontal line instead of peak.
That's true, right? So first peaks merge, then so the oscillations become smaller and smaller, and simultaneously the average level of these oscillations increase. So there is a difference between largest conductance in Coulomb blockade regime and average conductance at high temperatures. Do you want a hint? Just several transparencies back. It's hidden in this transparency.
There is a second electron. Right?
Yeah, it has something to do with second electron, but what's precisely the mechanism?
So here we see the occupations, the blue boxes, and their steps. So if there's much, then the occupation at the next charging energy is not zero. So we can have two channels.
Okay, no, you go in a good direction. Let me just formulate a few purposes. So if we are at low temperature and precisely at the peak, the situation is like this. Electrons tunnel one by one. There is a possibility for an electron to come, but it blocks the second electron. So it kind of spends a half time in the island, back, forth, and by this half time, the transport is blocked for other electrons. If temperature is high, everything is possible. All processes are possible. So electrons kind of do not know about each other, right? So that gives a factor of 2. If junctions are of the same, or if the conductances of the junctions are of the same order of magnitude. Okay, that we have. Right, something about the scale. It's popular nowadays to talk about moral dilemmas in science. So let me also formulate a small control question in the form of a moral dilemma. Suppose you have a friend who's experimentalist, and he kind of show you similar curves, experimental data, and you look at conductance scale, and here you notice that it's eventually inverse ohm. Do you still have a friend?
I think it would be more normal to use a conductance quantimeter.
What's normality? Experimentalists are particular people anyhow. But it's about reality, right? It's about reality. It's normality and reality. Normality is our norms, our vision, and that's reality. So reality is such that it's Coulomb blockade system. This Coulomb blockade system, which means that conductances involved should be much smaller than conductance quantum. Only this will give us Coulomb blockade. So if you look at the axis and if you see values of inverse ohm, that's about 4 orders of magnitude bigger. It cannot be Coulomb blockade. So there is some whatever moral or understanding flow with interpretation. Fine. So we understand the scales. It has to be here many times much less than conductance quantum. Much less. Let me talk about yet another manifestation, and this is a kind of complementary situation. So now we fix gate voltage and we increase bias voltage. So what do we expect? First of all, at small voltages, we expect Coulomb blockade. No current at all. Then, okay, we exceed Coulomb blockade threshold. The current goes on. It increases with increasing voltage. That's also okay, because it should become ohmic at some stage, right? If voltage is sufficiently big, then you expect that charging energy is not important, and the ohmic behavior. However, there are some peculiarities at this curve, discontinuities at small temperature. And well, it's about philosophical question about existence and visibility. Say if the junctions are the same or about the same, you know that peculiarities are there, but you can hardly see them. They are very small cusps. But if the junctions are very different, and I guess for this example, I have taken the ratio to be 50. Then these peculiarities are clearly visible, so there are cusps, and they even form a little bit continuous steps. So this is real peculiarity, and there's a continuous step which is not really a sharp step, but kind of accomplishes the singularity. So can you guess what the reason of these peculiarities?
It must have something to do with the levels entering the bias window discretely.
Yeah, yes. It's not the levels, it's better to talk about charging states. There are no discrete levels here, it's a problem. Let me perhaps illustrate it with this diamond picture. Okay, there are diamonds where number of charges is fixed. 0 here, -1, -2. Good. So let me draw another diamond. A continuation of this tube. My question is, what are possible charging states in this diamond? So there's some transport in this diamond, but what are possible charging states?
-1 and 0.
In this one, it is adjacent to two Coulomb blockade diamonds with -2 and -1. So the conclusion is?
-2 and -1.
Yeah, very good. Very well. Okay, there is a diamond like this. And let me make yet higher diamond. So how many charging states are there?
3.
Precisely, right? -2, -1, 0. So that's how it goes. Now, if we just take a vertical line, you see how does it cross the diamonds. So there are peculiarities anytime, indeed, you open a possibility for yet another charging state. So this is called Coulomb staircase.
My question.
Yep.
If the tunneling rate at the lead is much lower than the tunneling rate towards the drain, then there's almost never a situation where there's an electron on the island, because as soon as it gets there, it goes off immediately.
No, if transport is blocked,
Oh yeah,
it cannot. Yeah, that's why these peculiarities become very pronounced if conductance is weak. So in this case, one of the junctions just prepares island in a certain charging state, but at some stage you just cross this threshold and you have almost a jump in conductance. Fine. Let me talk about fancy thing. Let me pay attention to the fact that we could so far leave with classical physics. We've been talking about classical states which differ by number of charges. And although we involve electron tunneling, which is in principle quantum phenomenon, we took it at classical level as rates of classical events, electron transfers. But there is quantum mechanics involved, and that theory formulated in the 20th century, as we know, is very democratic, or even I would dare to say libertarian. Right? So common joke is to compare classical physics, where everything is defined by laws, where all particles are governed by very strict rules. You can provide, draw an analogy between them and the kind of absolute monarchy dictatorship. While quantum mechanics is more like a modern pluralistic society, where everything is possible, everything is allowed, provided it's not forbidden by very fundamental laws, like energy conservation, conservation of particle number, and okay, if fundamental laws are not violated, then the particles, quantum mechanical particles, should always find a way to do what they want. Right. And tunneling is a kind of interesting manifestation of this principle. Good. So what I want to discuss is a single-electron transistor, simplest circuit we have considered so far, in the Coulomb blockade regime. In this case, it is impossible to put an electron to the island, owing to energy consideration. So single electron processes are strictly forbidden. Boom. How would you cheat about this? Well, there's a very simple way to cheat. You just cooperate with other electrons. There's still electrons in the island, and while one electron enters the island through left junction, in a short while, another electron jumps through the right junction. Finally, when poles come, it finds zero charge at the island. But energy transfer, electron transfer has occurred from left lead to the right lead. Good, it's called co-tunneling. So how to express it mathematically? It is a rate of complex tunneling process which involves two and some virtual states. So what was a virtual state for this process? This is a state with a charge in the island, right? You could kind of, the philosophy is that you could go to forbidden state, to virtual state, which is forbidden by energy conservation, but you could only stay there for a short time. This short time is defined by Heisenberg relation. We recall already a Heisenberg relation. So this time is inversely proportional to the energy difference between between the states. Right. That's why we have this equation for the rate. It involves both amplitudes, energies of and energies of virtual states. And that will give us the possibility to compute co-tunneling rate, the rate of this cooperative tunneling of two electrons. What's important to see? First of all, this rate is inversely proportional to both resistances. So it's a product of two conductances, right? So single-electron tunnel rate is one conductance. Here we have a product. We know that conductances are small in comparison with conductance quantum. So it is much lower rate. It is much lower rate. Also, it is their temperature is proportional to voltage cube. Why is it so? Because although the charge in this island after electron transfer is zero, there is some trace which kind of observable policeman can detect. What is a trace? Can you tell me? Electrons has come. Another electrons has left. But usually these energies and states do not match. So as a matter of fact, after electron transfer, there's some trace, there's electron-hole pair created. This electron-hole pair costs energy, and that's why available energy is smaller, and that's why the rate is smaller at smaller voltage. Okay, I think I told about co-tunneling. That's how they merge single-electron process and co-tunneling at the boundary of diamonds. Sir, I guess I'm done with Coulomb blockade. Sir, it was a long story, but I'd like to express once again my fascination with the simplicity of the story. We can start with very small assumptions, with very simple assumptions, very natural assumptions, and build up everything up to very concrete experimental predictions. Good. Thank you for your attention.